Hello and welcome to the second part of Lesson 4. And this one is really just a quick review of some new things in the Moodle site, as well as looking at some um, exercise cases. So I'm now logged in as Mr. First Last. So this is the user's profile, and it's basically just a fake student account so that I have the ability to look at the course from you, the student's perspective. So this video was made around the time Lesson 4 was being recorded, and it's actually the second video in this. The current one is currently uploading, and Lesson 4 has some PowerPoint slides associated with it, and some readings regarding pump selection, suction conditions, net positive suction head explanations, and a couple of lift station design manuals. You should certainly familiarize yourself with everything, but selection, suction, and NPSH explanation are probably the more useful readings in the short term. The two design documents you will need or you'll use later on in the course as needed. What I wanted to do is return to exercise set 2. Currently, that's right, I am a student, so I have not uploaded it, but here's the actual exercise, and you all have seen it, and we're supposed to prepare a summary of the article that's attached, and the article is a history lesson bringing water from the Los Angeles Aqueduct to, from the Owens Valley to Los Angeles. And it was a relatively large undertaking in its time, and the purpose of the aqueduct was to provide water supply for the city of Los Angeles to supplement the existing supply, and the city was growing. And so if you read this, it has some interesting photographs and interesting observations on some, for the time, relatively novel technologies. Okay, so Mr. First Last has already done this and has actually prepared his document. And so to do it, here's Mr. First Last's solution. So prepared in a memo format as required, and the purpose is the memorandum's a brief summary and review of the article history lesson regarding the design and construction of the Los Angeles Aqueduct. It is addressed to P.N. Gwynn from P. Oler Bear, and this memorandum will be delivered in about 6 years. The discussion section is the actual meat of the memorandum. So the article presents a brief history of the Los Angeles Aqueduct. It was built in the early 20th century. The system captures water from snowmelt in the Owens Valley in the eastern Sierra Nevada and transports that water to Los Angeles. The system is gravity flow, in that Owens Valley is considerably greater altitude than Los Angeles, and contains several electricity generating stations. So as the water is making its way to LA, it's also making electricity. Most of the system is open channel in either open trapezoidal channels or large bored tunnels dug through rock. Some portions are pressurized pipes that cross valleys as inverted siphons. The project itself involved construction of roads, rail extensions, concrete plants, and mining operations. It was, for its time, a huge engineering undertaking involving nearly all aspects of civil engineering, including land acquisition by both purchase and the legal concept of eminent domain. The techniques in engineering construction were used later in the construction of large dams in the western United States, including Boulder Dam, or Hoover Dam, which impounds Lake Mead just south of Las Vegas, and the Grand Coulee Dam, which impounds the Columbia River in Washington. I think it's in Washington State. It might actually cross from Oregon to Washington. Both of these two dams contributed to economic success of the United States since the 1930s, and the Grand Coulee Dam has been argued by some that it provided the electricity to smelt aluminum to make B-17s and B-29 bombers, which helped the United States contribute to the Allies prevailing during World War II. The aqueduct itself is a living example that encompasses most existing water transmission technologies except for pumping. The aqueduct has pressurized pipeline portions, turbines, open channel portions, and storage components. When compared to a modern gas pipeline, the principal differences are the working fluid and the requirement in a gas pipeline of compressor stations to maintain the driving force to transmit the product. Otherwise, in terms of scale, complexity, and importance, the two are essentially equivalent. So that was P. and Gwynn's memo, and now the memo needs to be uploaded to the website. So to do that, the Penguin chooses Add Submission, finds his file, which is right here, chooses Upload. Actually didn't check the file size. I guess I'll do that real quick. It's 57K. That should be a little bit smaller than 8 megabytes, so it should work. Save the changes, and it says draft not submitted. Then I have to press the submit, and once I press continue, no force in the universe can make it come back. And now it's been submitted for grading. At the time of this video, let's see, Thursday, September 6th at midnight. It's only 4 hours from now. By the time you see this video, that's going to be moved to midnight of Thursday. That's a mistake on my part. Okay, that's exercise set 2. And so everybody's happy. Well, perhaps. The next exercise is exercise set 3. This is your first group submission, so any member of the group can make the submission. The exercise set is here, and it's to interpret plan and profile drawings. So there's going to be drawings on this page right here, and we have several questions to answer. What's the direction of the design flow implied by the drawing in figure 1? If we look at the drawing and look very carefully, we see that the pipes have slope from the right side of the drawing to the left, and so the design flow is intended to go from that direction. Ooh, it didn't like that. Fine. Design flow is from right to left, and we would prepare that in a memorandum structure. Figure 1 indicates a drop at a junction box. What's the bottom elevation of the junction box? The junction box is this critter, and so the best guess of bottom elevation is going to be this value 2387.64, which is the flow line. So let me go ahead and so right there is the bottom elevation of the junction box, and it says the flow line is 2387.64. We get kind of a clue from this left-handed vertical scale. So we would provide a narrative as well as explain the arrow. What's the diameter of the conduits? It strictly states that these are 36-inch reinforced concrete pipes. 36-inch reinforced concrete pipes, so the diameter is 36 inches or 3 feet. And finally, what is the slope in percent of the conduits? Okay, two ways to determine that. One would be to actually take 2 points on the drawing and find the horizontal distance and subtract off the change in vertical distance. Or, in this particular case, the engineer has provided the actual slopes of the conduits, and they're sloped 0.05% in the direction from right to left, and so we would write 0.05%. and that would complete this exercise. So this exercise serves two purposes. One is to have you read the plans, but the bigger purpose is to test the group submission capability to be sure you can submit it as a group. So let me see, I'm not going to save those changes, but I'm going to go ahead and get Mr. Gwynn's answers. So his is a solution. Be sure it's the right solution. So Mr. Gwynn actually did the entire solution in the narratives and answered the various questions, and so that's ready for uploading. And so we were going to go ahead and create a submission. Add the submission. Save the changes. Make the submission and commit it. And hopefully first last isn't assigned a group, because otherwise it's going to be very confusing to the other members of the group. And that constitutes exercise set 3.